especially when you work in hazards, I feel like there is a societal obligation that we have as scientists to make sure that our science, our data, our information is actually used by people. It's one thing to have the science and to do the science, but until you communicate the science, it's not actually finished.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. In just a minute, you're going to be hearing from Dr. Wendy Bohan. Wendy is an earthquake geologist and a science communicator. And today on the podcast, we're going to be talking about how GNSS can be used to monitor volcanoes, measure snow depth and vegetation growth, how Earth observation techniques can be used to map the underlying geology, and Lidar as a teaching tool. And towards the end, we're going to move off and talk about science communication. So we cover a lot of ground in this episode. Just before we get started today, I want to say a big thank you to our sponsor, Regrid. So Regrid are the parcel data people for the US. So think of parcel data as being the legal boundaries of properties. And America is made up of these legal boundaries, and they have owners, they have assessments, they have current land use. And these boundaries surround everything: homes, parks, commercial buildings, farms, wild places, everything. And I think Regrid summarized this really nicely on their website. They say if it's not happening in the middle of a street, it's happening on a parcel. So if you're interested in this kind of data for the US, Regrid is the place to go. They have over 150 million parcel boundaries that covers 99% of the US population. And this is complete with standardized schemas, normalized land use classifications, persistent universal IDs, and over 120 property and tax assessment attributes. So a couple of things are worth noting here. Firstly, you can just go to the website and check this out. So if you go to app.regrid.com, they have a web application there, a web map. You can click around and get an idea of what the data looks like, the coverage they have, that kind of thing. And I love the fact that it's super transparent. So sometimes I go to these data companies' websites and have a look, and it can be pretty difficult to figure out what things cost, but this is not the case with Regrid. So if you're looking for parcel data for the US, I'll put a link to Regrid in the show notes to make it a little bit easier for you to find them. Hi Wendy, welcome to the podcast. Thank you very much for doing this with me. I realized that you have had a few health issues, and I'm just really grateful that you took the time to be with me and do this with me today. So this is going to be good. You are a earthquake geologist and a science communicator. Perhaps we should start off with an introduction. Would you mind just introducing yourself to the audience, telling us a little bit about how you became an earthquake geologist? And I think later on in the conversation, we can tackle the science communication bit of your work.
Sounds perfect. Thank you so much for having me, Daniel. So, as you said, I'm Wendy, and I actually started off as an actress. So, my undergraduate degree was in theater, and I did take some geology classes while I was there just because I thought it was really interesting. But I moved to Los Angeles from the East Coast of the US in order to be an actor. Not really because I wanted to be an actor, but I really kind of didn't want to get a real job. Anyway, I'd been a professional actress there for a few years when the Hector mine earthquake happened. So that was a magnitude 7.1 earthquake that happened out in the desert, but it was widely felt across Southern California, including in my little fourth floor apartment in Hollywood. And, I grew up on the East Coast. Earthquakes were pretty rare, and it was an experience. I mean, it was crazy. It was so loud. Car alarms are going off and the building is creaking, and we had a little pet rabbit that was screaming. Anyway, I was fascinated. And I was a bit of an adrenaline junkie, and I mean, there's nothing that really gets your adrenaline going like an earthquake, right? So I went to the US Geological Survey the next day and asked if I could volunteer. They said no, because turns out after a large earthquake that's felt in an urban area, they're a little bit busy. So anyway, I did go back and said, please, I'd really, really fascinated with this. I'd really like to help. And so I worked there as a volunteer for a little while, and I was there for a bit, and they said, you know what, you're actually kind of good at this. And so they hired me, and I worked in outreach and education for the USGS Earthquake Hazards Program in Pasadena. So eventually I became the head of outreach and education for that area. And then I decided that was what I wanted to do. I really could see firsthand how earthquakes impact people and how people that live in earthquake-prone areas really need to understand the science and what they can do to protect themselves and their families. So I ended up going back to graduate school, and I got a master's degree and a PhD in earthquake geology.
Wow, I'm totally blown away by that story. That is amazing. Like, what a transition, what a pivot. Incredible stuff. But I'm sure you hear that kind of stuff all the time, so I won't Go overboard. But would you mind explaining to me the difference between earthquake geology and seismology, please?
Absolutely. And I'm so glad you asked that because there's a lot of confusion about it. People are always asking me seismology related questions. And I work for an organization that does seismology work, which makes it even more complicated. But earthquake geology is studying how earthquakes impact the surface of the earth. So for me, I'm interested in looking at how the faults change the surface through time, what the impact of repeated earthquakes does to the surface of the earth, how we can map that, how we can understand that, and how we can use that to sort of look at the overlying form and understand the underlying structures. Now, seismology is really interested more in the seismic waves that come from earthquakes and using those seismic waves to look inside the earth, kind of like a telescope peering into the earth. So they're looking much deeper than I would. So I'm looking right at the crust along the surface, and seismologists are looking much deeper. But together we have the whole enchilada.
I realize you just finished saying that people are always asking you seismology questions, and now I'm going to do the same thing. Are seismologists only interested in using the waves that a earthquake emits, or can they use other waves? Can they manufacture those waves themselves in order to remotely sense what's happening inside the earth?
Yeah, such a great question. So there is active source seismology and passive source seismology. So passive source seismology are the waves that we get that we don't have to create ourselves. So that could be from earthquakes, that could be from construction, people moving around, volcanic eruptions. Anything that shakes the surface of the earth basically puts energy into the ground, and we can see that on the seismic instruments. Now, active source seismology is where we actually are putting the energy in the ground on purpose in order to see something specific. So in some cases, there's these little plates that people will put out along with a line of geophones or small sensors. And you'll actually use a sledgehammer to hit that plate because you want to see what's happening in the near surface, near where those geophones are. Some cases we'll use explosions to do that, or air bursts if you're trying to look at things underwater. So yeah, we use all sorts of different things to look inside the earth. And seismometers are amazing. They can detect all sorts of things. They can detect tornadoes and hurricanes. Seismometers are amazing instruments.
Wow. I am going to have to get a seismologist on the podcast and talk more about some of the stuff. You're mostly interested about what's happening on the surface of the Earth. At least that's my understanding from the conversation so far. How do you map that? Like, what instruments, what techniques do you use to look at the surface of the world and see how it's moving and how it's changing?
Well, let's sort of start in a macro kind of way. So there are GPS instruments all over the surface of the earth, right? And usually when people think about GPS, we think about using them, in our cars or on our phones, trying to locate where someone is. But for us, we use GPS instruments to see how the surface of the earth is moving through time, both vertically and horizontally. And so that can be used, for instance, to figure out where stresses and strain is building up inside the crust. So there's something called the Plate Boundary Observatory, which are hundreds and hundreds of GPS instruments across the west coast of the United States. And when the ground is moving, and say there's one GPS instrument to the west and one GPS instrument to the east, if they're moving apart from each other, then you know that there's a fault in the middle that's accommodating that motion. And eventually there's going to be an earthquake on that fault. So GPS instruments can help us to quantify exactly what's happening with the surface. Same with volcanoes. So if we have GPS instruments on a volcano and the volcano starts to inflate or starts to, magma comes up towards the surface, those GPS instruments will start to move away from each other. You can think about it like if you put two dots on a partially inflated balloon and then you start to blow that balloon up, think about how those dots would move in relation to each other. So we can use GPS instruments to do all kinds of things like that.
So, getting back to that network of GPS instruments you're talking about that spread across the states, what kind of density of these measurements do you need in order to sort of give you a clear picture of what's happening? How close do they need to be together?
Well, we always want and need more instruments, right? Because the more instruments that you have, the better the data that you're going to get. But really, even just one instrument can give us a lot of information about how the ground is moving. So, say you have an instrument in the San Joaquin Valley. So, there's been subsidence in the San Joaquin Valley from groundwater being removed. And so, if we just had one instrument there, we would still be able to measure some amount of subsidence that's going on in that valley, or even the recharge that comes after a big rain starting to fill in that aquifer. So even one instrument can give us really critical information. Now, if we want to kind of measure the whole dynamic system of the Earth in that area, then you're going to want a bigger network of GPS sensors. If we're looking at how the faults are moving or how the plate boundary is moving, we're going to want to have hundreds of seismometers and GPS instruments out there to look at that.
I just want to make sure I've understood that correctly. So you're saying with one of these, a GNS base station positioned above an aquifer, you can measure the rise and fall of that aquifer.
Yeah, yeah, like it's like the Earth breathing kind of, yeah.
Wow.
And GPS stations can be used to measure lots of other things. There's GPS IR, which helps us to look at things like snow depth. So if you have GPS instruments that are in a remote location and you have snow that falls, you can actually use the signals that we used to want to get rid of. You can use that to see how that's changing. So we can use GPS sensors to look at soil moisture, to look at the depth of the snow. We can look at vegetation and how vegetation is growing. So GPS instruments are more than we think of, getting from just here to there. In fact, I worked on a study in South America where we installed campaign GPS stations across parts of the Andes Mountains. So campaign GPS stations are where you go in and you put a monument in, but you don't leave the instrument there. You come out with the instrument for a few days or a week and gather enough information to be able to place it very well, and then you go back over and over through time. This is to help cut cost because, of course, the instruments are really expensive. But what we were looking for was kind of the interaction between climate and tectonics. And in this case, we were looking at how the glaciers melting was allowing the mountains to rebound. So, isostatic rebound, the ice is heavy. As the ice melts, the mountains rise up, and trying to figure out why the mountains are rising due to isostatic rebound versus why the Andes Mountains are rising due to the subduction zone and tectonic processes that created the mountains in the first place.
Wow. I feel like I'm going to be saying wow a lot during this conversation. I want to just jump back in time because you talked about measuring, I think, snow depth and vegetation. And I just want to make sure I've understood this because it sounded like you're talking about using the multipath signals, bouncing off the environment around these GPS stations and using the change in those signals. I get maybe the angle of reflection to figure out, oh, like the ground is higher than it was. Maybe that was snow, or maybe that is vegetation that is growing around the stations. Am I on the right track here?
You've got it perfectly. Thank you for filling in the gap that I left there. Yeah. One of the things I really love about science is how creative people can be. So, we're always processing data and trying to get really clean signals, and some very clever people said, "Wait a second. I bet there's a signal. I bet we can learn something from the data that we're getting rid of." And so they started looking at these other multipath signals to figure out what that could tell them. And that's what they learned, is that as the angle changes, the reflection from the surface changes as it comes up to the GPS station. That can tell you a lot about what's happening in the near surface environment near the GPS.
Yeah, I don't want to belabor the point too much here, but I'm wondering if you could give me an idea of what like a meaningful amount of movement would be in a geologically active area. Like what kind of movement are we talking about before some alarm bells start going off somewhere?
It depends on the environment and where you are. So, if you have centimeters of change on a volcano, everybody starts to sit up and pay attention. The San Andreas Fault, for instance, is moving at about 55 millimeters a year. So we expect for the stations that are around there, obviously they're attached to the ground, right? So they should be recording about that much differential movement between, say, one that's on one side of the San Andreas Fault system and one that's on the other side. So that's like 5 centimeters a year. So that's a significant amount of motion, but that's what we would expect.
I'm guessing somebody is looking at this data, looking at how the Earth is moving and deforming and adjusting the coordinate systems that we use, but based on this. I wonder if you can speak to that at all?
Oh my gosh, I don't know so much about that. I just know that because, when we install the GPS stations, we install them in a particular place. And since we are looking at how exactly that place is moving, our coordinate system is also moving through time. And so that needs to be adjusted. The last time I was working significantly with GPS data, we were using the 1984 coordinate system, and I imagine that's pretty outdated by now. But I don't know how they do it or when, but it's a complex problem when the thing that you're studying, like the actual system that you're using as the underpinning, is also changing.
So I know that you have this great story about using Earth observation satellites to map fault lines, and I think maybe that this next question might be a good segue into that kind of technology. What do you think about some of the developments with synthetic aperture radar and some of the things they can do now in terms of measuring the surface of the Earth to very millimeter accuracy? Is there an opportunity to use this kind of stuff in your work?
Oh, yes, and it is so, so neat. When earthquakes happen, they change the surface of the ground. Almost all earthquakes. Some are so deep that they don't, but let's just consider kind of a normal earthquake. You're going to have some deformation of the ground. And what these satellites can do is map out exactly where that deformation happened, whether it was vertical or horizontal or exactly however that fault system moved. So you're able to very quickly figure out exactly the geometry of that fault. And so those maps can also be really helpful in sending in geologists to do mapping of the surface, especially if there's significant deformation like cracking or liquefaction, things that have really changed the surface. So the remote sensing tools that we can use are really helping to facilitate the boots on the ground geology that we often think of as kind of the core of the field. That's not the case anymore. Now we have the on the ground geology, and we also have the in the sky geology, which is amazing.
Yeah, that's really incredible. So you've got a interesting story about using the spectral signature of rock to map fault lines. Would you mind sort of walking myself and the listeners through this story?
Oh, sure. So for my PhD, I was working on the Karakoram Fault Zone in northwest India. So it's on the southwestern edge of the Tibetan Plateau, and this is a really long fault. It's about the same length and the same sense of motion as the San Andreas Fault, but it's very, very hard to get to. It's in very remote areas, and I was working in Ladakh, India. And so this area has been difficult to work in for a whole lot of reasons. For one, the topography is just beyond belief. So K2, the second tallest mountain in the world, was in my field area. Most of the areas we were working were far above 15,000 feet. So there's not a lot of air, there's a whole lot of rock, there's not a lot of access, and there's a lot of geopolitical strife in that area because it's right on the border between India, Pakistan, and China. So there's a lot of contested area. Because of that, geologists have not been able to access large parts of that region. And so the geologic mapping was sparse. Some areas were mapped in great detail and done very well, but then there was a lot of inference. And so a lot of the maps didn't match. Well, it's really hard to do kind of a large scale tectonic study of something when you don't actually have a base map. So I was lamenting this fact with some of my friends from grad school, and we were sitting around having a couple of beers or whatever. And one of the guys goes, "Wow, you know, we can map the surface of Mars, the mineralogy of the surface of Mars. Why don't you just use the Aster and map the Himalayas?" And I was like, "What? What are you talking about?" He's like, "Yeah, the Aster instrument on the Terra satellite. You know, you can figure out using all of the different spectra what exactly the minerals are there. And of course, minerals are the building blocks of rock. So if you know the combination of minerals, then that's going to tell you what the rocks are. And then you can make some educated guesses, some assumptions about the bedrock." And I was like, "Oh my god, let's do this." So I went to the Mars Space Flight Facility, used some of their codes and adapted them along with some of the co-authors on these works, Olga Tripathi and Chris Edwards and others. And we basically mapped that area of the Himalayas using the Aster instrument on the Terra satellite. So the Aster instrument is it's the Advanced Spaceborne Thermal Emission and Reflection Radiometer. So it basically is a multispectral imager that collects data at different resolutions in the VNIR, the SWIR, and the TIR, so all these different spectral bands. And I was interested in the thermal infrared because that's what you can use to basically map the mineralogy. And it was really amazing because, you're doing this and you're like, this is all very theoretically sound, and I absolutely believe this, but I really want to check because I think that this is, granite based on the spectral bands and the mineral composition. This must be granite. I'm going to call this granite, but I want to check. So what we did have access to a lot of these areas. And so we would go in and we would collect a hand sample and GPS locate that exact sample. And so then I had all of these samples from across my field area, and I took them back into the lab and I scanned them using an instrument that collected the same kind of information. So then I could compare the data from the Aster satellite to the data that I had collected in the laboratory, and I could see that they matched, and I could see the rock in my hand, and the rock is granite. And I'm like, okay, now I have much more confidence in this method. I can see that the granite signature is the granite signature is the granite rock. And so then I could apply that same signature with some significant amount of confidence to areas that I wasn't able to access. that had that same spectral signature. Does that make sense?
Total sense. Total sense. Thank you for walking us through it. But once you know about the mineralogy of a certain area, what does that tell you about the geology? How do you relate that back to mapping fault lines or mapping what's happening underneath the surface?
Perfect. I love it. So the Karakoram fault is a strike slip fault. So that means that it's sliding horizontally. And that means that anything that's along it is going to be displaced. So if you think about, say, a road that's driving over the San Andreas Fault, okay, and then there's an earthquake. One side of the road is going to move over to the right if you're just looking across it, and the other side is going to look as if it moved to the left. And so those are called piercing points. And that can happen with roads or fences, or say if it was a basaltic dike or the contact of a
River?
rock formation. Rivers, absolutely, yes. All of those things are going to be offset by motion along this fault. So, using these geologic maps and using the topographic maps, you can go along and you can find these piercing points and match them up across the fault to figure out how much horizontal motion has happened. Then, if you can actually date, say, that dike or when the river moved or some of the landforms that were created by motion along the fault, you can start to get an idea of how much motion there has been on the fault over a certain period of time. Dates equal rates.
I got to stop myself from saying wow again. So I won't do it. But all this kind of mapping work, it feels like foundational work, foundational science, things that maybe should have been done. When you think about mapping the world in this way, understanding how it's moving, where it's going, fault lines, the underlying geology of things, how close are we to being finished?
The world is wide and wonderful. There's a lot of things to know. There's a lot of things to map. I mean, there's so many places that we just haven't had access to, and a lot of places that we have had access to that we can now explore with new tools and get all kinds of new data. And so, how much is done? I mean, a lot. We've learned a lot. But if you think about kind of the work that I do, this geomorphology, earthquake geology, this really just started back around 1906. The 1906 earthquake was kind of the inception of this type of work. So it's only been, 100 and some years. So we have a lot of work left to do.
So I'm constantly hearing people say what gets measured gets managed. When we talk about ecosystems, I think this makes perfect sense. Does it also make sense when we talk about geology? Like, can we in any way, shape, or form manage geology? What would we gain if from doing all this mapping work?
Oh, yeah. So the first way that I think about it is science for science's sake is always important, right? So it's anything I learn about the Karakoram Fault in India, I can then apply to other continental systems. I can use that knowledge in other ways in other places. But more specific than that, especially with something like geology or earthquake hazards, that has a direct impact on people and their lives and their livelihood. And so by studying faults and how faults work, measuring how quickly faults are moving, how stress is distributed in the crust, how quickly we have earthquakes on these different types of fault systems, that has real world implications for real people because people all over the world live in earthquake prone regions. The more we can understand about the hazards, the better we can quantify those hazards, and the better we can communicate those hazards, the safer our cities and our citizens will be.
Yeah, I mean, that makes perfect sense to me. Absolutely perfect sense. I want to move a little bit closer to Earth. So we've been up in the space looking down using these remote sensing Earth observation instruments. If we come a little bit closer, what about LIDAR as a tool for mapping things? We're talking about deformation. We're talking about those where we can see clear fault lines that have cut through objects. And I think you call them piercing points.
Mhm.
To me, LIDAR seems like it might be a good tool for this. Is that something that you use in your work?
Oh, absolutely. LIDAR is just the perfect tool for looking at the topography and the surface of the earth and how that's changed because tectonics, there's basically this battle that goes on the surface of the earth between tectonics, which build the ground up, and erosion, which wears it back down. And so LIDAR really gives you the input into those systems that you need in order to understand how the landscape is evolving through time. And LIDAR is great because it actually gives you 3D information. So instead of, say, like a Google Earth image where you can get a lot of data and information from that, you see, say, I don't know, like a cliff next to the ocean and there's a fault there and there's a hill. You don't know how tall the cliff is. You don't have any idea whether or not there's a little slope on the fault called a scarp. You don't know what the hillside is like, but you can get some information. Lidar gives you all of that information and three dimensions. So you can see exactly what's happening. You can make quantitative measurements. And so you can get a better idea for what's happening. We actually did a scan of the San Andreas Fault in Southern California called the B4 project. And the idea was that it was getting information on the fault system before the next big earthquake. You get it? You get it? So we scanned the whole San Andreas from the Salton Sea all the way up through Parkfield, so Southern California, all the way up through Central California. And it's this giant repository of really, really interesting information about that fault system. And now, after the next earthquake, we'll be able to go back and see exactly how the ground changed as a result of that earthquake, whenever it may happen.
So I've heard some archaeologists talk really passionately about LiDAR, and they talk about doing something called digital deforestation. Is this a practice that you have as well?
Oh, yes. So when LiDAR basically, I'm sure you know, but just to go through the basics to set the scene, it could be in any kind of airborne system, a drone. Let's just say that it's in a airplane. So you have the LiDAR system and you have the GPS in the plane, and then you have GPS on the ground. So you know exactly where the plane is in space. And then it flies along, we'll say it's flying along the fault in this case, and the lidar scanner is scanning back and forth across the ground, and it's just hundreds and hundreds and hundreds and hundreds and thousands of points of this laser light going down. And so even if you're in an area that's forested, you can think about it like sunlight flickering through the trees. Some of it is going to hit the floor of the forest, right? Even though some of it gets stopped. So we call the first laser hit that comes back to the plane the first return, and generally if you're in a forested area, that would be the top of the tree. Then you'd have a second return, which is, say, bouncing off a limb a little lower down. A third return would be maybe bouncing off a leaf. Eventually, you're going to have the final return, the last return. That's the ground surface. And so, if we get rid of all of the returns except for the last return, that's going to show us the surface of the ground. This has really been a critical tool in places like Oregon and Washington State because they have lots of fault lines, but they also have lots of thick vegetation. So by doing virtual deforestation, getting rid of all of those returns except the last return, we're able to see the ground surface and much more easily locate where the faults are likely to be.
So I want to move on and talk about your work as a science communicator in just a second. But see, LiDAR is such a wonderfully, it creates such wonderful sort of visual representations of the surface of the world, or it can anyway. I completely understand that we can use this as data, so we can measure and we can do analysis on that by itself. But I'm thinking also that when we create these 3D models, they would be really good storytelling images that we could use to help explain to people what's going on. Is this ever something that you do or or perhaps have done before?
Yes, I worked on a project using LiDAR as an educational tool with the idea that people are used to looking at maps, say like Google Earth, but they get distracted by things in a Google Earth image. Just in your mind, sort of shut your eyes and picture a Google Earth image. What are the things that you think about? It's probably the roads or the houses, the land use. Is it farms? Is it trees? You're not thinking about the shape of the ground underneath all of those things. And so by using a LiDAR image, as opposed to, say, that Google Earth image, a satellite image, what we can do is make the ground the most obvious thing. And so that really helps, especially novice learners, to focus on the landscape and to start to make critical observations about the landscape. Like, look at all these linear hills right here. Or, wow, look, there's a line going through the middle of this image. And on one side, there's hills, and on the other side, it's flat. That would be, say, a fault. So by using LiDAR as a teaching tool, we are able to get people to really concentrate on the things that we need them to know and understand. Again, looking at the overlying form to determine the underlying structure.
How successful has that been? Like, I think that these images that you can create using LiDAR are fascinating. But I know a little bit about LiDAR. I'm used to looking at this kind of data. When you show it to someone, do they get that? How much coaching do they need before they can sort of start looking at at a data set like that in that way that you're talking about?
It depends. So the LiDAR images are usually in grayscale. You can put different things on top of them, but usually they're just in grayscale, and they're fairly intuitive. It takes people a few minutes to get used to looking at that new type of data. But in general, they start to go, oh, okay, that must be a house. Oh, lake. All right, that's a hill. And when we were doing these experiments, we didn't give them any background about what they were looking at, and they figured it out really quickly. The exception to that would be if you're looking at, say, imagery of like a crater, because some people, depending on the sun angle, they'll see a crater as a hill instead of a crater. And so then you have to kind of turn it around to get them to orient their eyes to the sun angle that their brain is expecting.
Yeah, I've fallen for that before. It's like those magic eye images, where you look at if you look at it for long enough,
Hmm.
you see a dolphin. Yeah, I'm terrible at that. Terrible at it.
Yep.
I want to talk about science communication because this is another huge part of what you do. And so you're a scientist. What is attractive to you about the communication side of it? I mean, you have a PhD. Most PhDs I know that they don't really want to necessarily talk to people. They're really into doing their science, to doing their work, to looking at the data, to being creative in that way. Why is it that you have decided to focus on the communication side of it?
Part of it is, I think, is where I came from. I saw very early in my career how important it was to communicate with people that need to use the science, whether that be a lawmaker, a religious leader, a mom at home with her kids. Especially when you work in hazards, I feel like there is a societal obligation that we have as scientists to make sure that our science, our data, our information is actually used by people. It's one thing to have the science and to do the science, but until you communicate the science, it's not actually finished. And so the organization that I work for is primarily funded by the National Science Foundation. So it's taxpayer dollars. We owe people. They are paying my salary. It's my job to tell them why the work that we do matters, how it affects their daily life, and how we're using this information to help keep them safer. So I really feel like the communication part is something that was critical to me personally. And I see every day what a difference it makes to people. Little things. There's a lot of people that move out to the West Coast from other places. There's a lot of military families out there, for instance. And I'll get emails from families that have moved out there and they're terrified of earthquakes because it's so far out of the realm of their experience. And so by just spending maybe 5 minutes sending them an email and some information, I can help to alleviate some of that anxiety. And that, to me, really is the best part of my job. Like I can make a difference in somebody's life in a real way. And that's really important to me.
Okay, so a couple of questions here. The first one is, should all scientists also consider themselves storytellers or communicators?
No, we all have skills in different areas. And I think that we all have different levels of comfort. But I do think that all scientists should be able to share their science in the way that works the best for them. So that may not be giving public talks. Maybe that's writing a blog. So do I think all scientists should communicate? I guess the answer is yes, but I don't think everybody needs to communicate publicly. I don't think everybody needs to be on TV. I don't think everybody needs to be doing everything. Not everybody's going to have skills or interest in those areas.
Yeah, totally agree. I guess my next question is, what do you do when it's inconvenient? So science is just science, right? Facts are facts. This is what is happening. This is what we believe based on the data that we're looking at, the models we've run, the experience and knowledge we have. This is where this situation is going. That can be pretty inconvenient sometimes. What do you do when you run into a situation like that?
Well, the first thing that you have to be is honest. It's very difficult in communities where they've just had a large earthquake to have to tell them that they're going to have more earthquakes. They're going to feel more shaking. That's what's going to happen though. People need to know. And sometimes it is a terrible to be that messenger, and that's also our job. And we can communicate that in a way that is compassionate and empathetic and helpful, right? So part of it is about the messaging. You don't want to be like, oh, you got to panic. There's going to be more earthquakes. It's like, okay, you know what? This is normal. There was just a large earthquake. That was terrifying. I bet that was really scary. This is probably what you're feeling right now. And there's going to be some more earthquakes. That's normal. It's expected. Be ready for it. And when it happens, do X, Y, and Z. So you want to give people some kind of actionable item, right? So that they can have some agency, so that they can feel some amount of control. But the data is data and you have to tell people.
When you think about the way that climate change has been communicated, what do you think of that?
There's been a lot of people doing a lot of really amazing work in climate change communication. It's obviously been very politicized. I think one of the things that needs to happen now, I think one of the paths forward is we have to give people hope. For so long, it's been just trying to get people to see that it's happening. And so now I think most people see and recognize and understand anthropogenic climate change. And so now we can focus on, okay, what are the solutions here? What are the things that we can do? Because, we as a society, we as the human race have done amazing things. I mean, we have we have cars on Mars right now. We have a helicopter on Mars. Like, we can solve hard problems. And so we need to have people work towards this problem with that same mindset that we can do hard things. This may seem impossible, but we have done impossible things before. So instead of, the end is nigh, we all are going to die, like, we need to change it and start focusing on solutions.
Thank you very much for that. I realized that was a tough question and not necessarily within your ballpark, but I thought as a science communicator, it would be really interesting to hear from someone like you that is used to trying to communicate complex problems, complex scientific understandings to people.
Yeah, it's hard. The climate change issue is difficult, and I really am very in awe of people like Catherine Hayhoe and others that have dedicated their life to getting the message out, to really speaking to people's minds and their hearts. Not everyone can engage with the scientific facts in the same way because we make decisions based on our values and our belief systems. If you don't understand people's values and belief systems, you're not going to be able to communicate with them in an effective way. And so there's a lot more of the social science in communication than I think people realize.
So I'd like to try and round off the conversation here. So you have this really incredible background. You were an actress, and you've got a PhD, and you've done science, and now you're almost like the front person for this science communication that you're doing. What's been the most rewarding thing for you? Was it the science side? Was it the communication side? Is it a mixture of both things? Like, yeah, what do you think of it when you look back at your career so far?
It's a mixture of both. There's something really, really incredible about generating new knowledge, finding out things or solving problems that nobody has ever solved before. There is something really richly rewarding about that. And for me, as I was, finishing my postdoc and I had just had two babies, twins, not two babies at different times, and I was like, what am I going to do? And I had to have a real sit down with myself and be like, okay, what do I want out of my life and career? And for me, I know a lot of really amazing scientists, right? Like, so many smart, creative people that are working in all these spaces. And I was like, I think I can be, with my skill set, the most impactful in this other sphere, the science communication sphere. And I do find great joy and great rewards from that because I do feel like I make a difference. And so here's an example. A few weeks ago, I was giving a talk to a fifth grade class about earthquakes and what it was like to be a scientist. And, as I was logging off, I hear this kid go, "That was awesome. I want to be a scientist." And that was one of the best moments of my career because I thought, you know what? That kid, maybe this changed something for him. Maybe this changed something for that one kid. And that means something to me. So, the science is great, answering those problems is great, traveling the world is great. And making a difference in the life of a fifth grader is amazing.
And it sounds like you haven't had to choose between one or the other. It sounds like you've done both. Hey, Wendy, I really want to thank you for your time. I realize you haven't been feeling the best, and I'm just so grateful that you took the time to do this with me. I really enjoyed the conversation.
Thanks so much for having me.
Before I let you go, where can people go if they want to reach out to you, if they want to learn more, if they want to continue this conversation?
Oh, yeah. So I have a website, drwendybohan.com, and you can go to my company's page, www.iris.edu. So IRIS, not the IRS, www.iris.edu. That's the Incorporated Research Institutions for Seismology.
Wonderful. Thank you so much for your time. Really appreciate it.
Thank you.
So once again, a big thank you to our sponsor, Regrid. If you are looking for parcel data for the US, regrid.com would be a great place to start. I'll put a link to them in the show notes to make it a little bit easier for you to find. So I really hope you enjoyed that episode with Dr. Wendy Bohan. So Wendy talked about a few subjects that we've covered in depth here on the podcast before, and the first one was GNSS. I think during the conversation we referred to this often as being GPS, but in actual fact it was GNSS. So Global Navigation Satellite Systems. In the show notes of this episode and in the email we send out, you'll find a a whole bunch of extra information about this. I'll also put links to previous episodes that cover this topic in a lot more depth. Nothing to be afraid of, but just a more sort of in-depth look at what is global navigation satellite systems. What do they do? What do they consist of? And how do they work? We also talked very, very briefly about SAR, so synthetic aperture radar. If you go back in the archives, you'll find an episode called An Introduction to Synthetic Aperture Radar. This is a really good introduction to it. So if you already know a lot about this, it's probably not for you. But if you're just curious and want to understand a little bit more and want a beginner's guide to it, this is well worth checking out. Wendy also talked about the B4 project. So this was the Lidar scan of the San Andreas Fault. And this is freely available on a platform called Open Topography. So Open Topography is like a data warehouse for topographic data. And we've actually covered this on the podcast before, so there'll be a link to an episode called Open Topography in the show notes as well. We've also talked about LiDAR in depth as well from different platforms. So yeah, I think I'll include links to episodes that you might find interesting. Just on a side note here, when I hear myself mention these episodes and these different resources, they're becoming quite extensive. So of course there'll be links attached to the episode that you're listening right now, and that you'll be able to click through to them. But I think a better option might be, if you want more information about these topics, is that I'm putting a lot more emphasis on our email newsletter, and there'll be a link to where you can sign up to that in the show notes of this episode as well. And this just gives me a few more options in terms of including information for you without overwhelming you. And of course you can look at it whenever you want that way. And it might just be a little bit easier to access some of the data and some of the resources in email format. Okay, that's it for me. That's it for this week's episode of the Mapscaping Podcast. As always, you're more than welcome to reach out to me. You can find me on social media. I'm most active on Twitter and LinkedIn. But increasingly, I think email is the way to get a hold of me. Again, I'll put a link to our email newsletter in the description of this episode, and you're more than welcome to sign up. No spam. I don't like it just as much as you don't. So try it out. If it's not for you, just unsubscribe. Okay, I'll be back again next week. I hope that you'll join me then. I'll see you then. Bye.